P. So what we're doing here, we're just summarizing what we did last time. We're talking about the equations of motion for uniform motion. The equations of motion for uniform motion can be written down as x naught plus vt, which when plotted in a graph of x versus t, you get a straight line with a given slope, the slope being given by the instantaneous velocity and the intercept given by the initial position. So you have to worry about problems like that, okay? There's problems that are very simple to solve, okay? And there are problems that are more difficult to solve. We have this whole gamma of problems that uses uniform motion, the concept of uniform motion. Very simple and very difficult problems, okay? Very simple problems, okay? Let me just make a list of the types of problems you will see for uniform motion. Okay. So one type of problem is the simplest of all. Given x naught, v, and t, find x. That's one type of problem that you're going to see out there. That's the simplest one that you are going to see. Okay. Find x. And then you can do something a little bit more different, right? Instead of giving x naught, v, and t, you can be given x, v, and t and find x naught, right? Given x, v, and t, find x naught. You can also, given, x naught, let's say, x naught, x, and t, find v, right? Given, another one, given x naught, v, and x, find t. So you have these combinations of problems, okay? And then there are problems that are a little bit more difficult. The simplest, okay, the simplest of types of problems that you see out there, the simplest types of problems you will see out there are the following. Okay, given. Then you have problems that are more complicated. Then you have problems that are more difficult, okay? So which other types of problems would be more difficult? Let me give you an example, okay? Given two cars moving, two cars in uniform motion, okay? One being ahead of the other, but moving slower, okay? Find the position that let's say, given two cars in uniform motion, car 1 and car 2, right? Here you go. Car 1 and car 2. Let car 1 be ahead of car 2, but moving with V1 less than V2, okay? Find the position that have given two cars uniform motion. Okay, I gotta put another important information here. Uniform motion and moving in the same direction. Okay. Given two cars, uniform motion, car one and car two. Okay, and moving in the same direction. Let car one be ahead of car two, but moving with a velocity that's lower than the velocity of the other one. Then the velocity of the other one. Here you go. V1 less than V2, right? Find the position that the two cars will, find the position that car two, let's see, car two will catch up with car one. Okay. Given two cars uniform motion, car one and car two, and moving the same direction. Here you go. Here you go. There's one more important piece of information. With moving the same direction with non-initial positions. Initial position x01 and x02. Okay, so here you go. We're going to solve this problem. Try to picture what I'm asking here. I'm going to make a drawing as well. Let car one be ahead of car two, but moving with a speed, with a velocity that's lower than car two. Find one. You go. I'm going to make a list here. The position that car one will catch up with car one. Okay. The instant of time. The instant of time. The car two will catch up with car one. Okay. We can solve this type of problem, and that's what I'm going to do. But I'm going to do even better than that. You know, instead of asking to solve the position first, I'm going to ask you to solve the instant of time first, and then you can calculate the position that car two will catch up with car one. Okay. Let's visualize this problem. The first thing that you gotta do is to visualize this type of problem. Okay, solution. Then you can put numbers in there. Let me show you what exactly I mean about that. Let's see. I'm gonna take advantage of this axis here. Okay, and here's gonna be my car. I'm going to put here car one. Okay. Going back to my given two cars, uniform motion, move the same direction with no initial position. Let car one be ahead of car two, but move with constant velocity that's less than the velocity of the other one. Okay, so here you go. Here's the initial position of car one. And then I'm going to put the initial position of car two is somewhere around here. Okay. That's how it looks like. With one very important difference. Okay. What's the important difference here? The important difference is that car two, despite being behind car one, is moving with a velocity that's greater than the velocity of the other car. And we denote the velocity by those arrows here. They're all moving the same direction. Here is V2, right? And here is V1. Because V1 is moving fast, car 2 is moving faster than V1, eventually it will catch up with car number 1, right? That would be the slide at time t equal to 0. I'm going to put it here. Here you go. Time t equal to 0. time t equal to 0. At a later instant of time, we're visualizing the problem. That's what we're doing. This distance here is going to grow smaller, right? So they're both going to move a little bit more to the right, But car number 2, can you picture that? Is going to be closer to car number 1. And that I'm going to call T1, instant of time T1. Okay. And later on, at some unknown instant of time that we can find out, right? They are going to be collocated along the freeway. Here you go. Let me do it like that. Here you go. And then I'm going to do even something else too. You know what? I'm going to, they're going to be collocated along the x-axis. I'm going to put it here. So they don't overlap each other, right? Here you go. Okay, that's the condition that we are going, what's going to happen here? Okay. X2 equal to X1. No, it's not X0, it's X2, right? Oh, and let me fix what I did there too. So I made a mistake in my drawing. Let's fix that. Okay, at this instant of time, V2 is still going to be greater than V1. And that's going to be instant of time 2, right? Okay. Here shouldn't be X0. Here should be X2. Okay. And here should be X1. There should be X0 and X1, X0 1 and X0 2, because it is at time t equal to 0. That should be the final position. The final position means the position at the instant of time t1, car 1 and car 2, right? And here you go. The position of car 1 and car 2 at the instant of time t2. Okay. So what we are asking here, what's the instant of time? What's t equal to 2 to t2 whenever x1 is equal to x2? Okay, that's the type of problem that we want to solve. And you want to know also the position of each car. Okay. Everybody got the idea? We want to know T2, the instant of time that one car catches up with the other one, and the position as well, that they catch up with each other. Those are a little problems that are a little bit more difficult than the other ones that I summarized here. This problem here. Let's do that together. It's not a quiz, it's just an example so you can get familiar with problems that are more difficult. So we are going to use as much info, we're going to extract as much information as I can from this problem. Okay. The first piece of the information is that you have two cars. Both of them are moving with constant velocity. That's the first piece of information. Piece of information 1. Both cars are moving with constant velocity. What does it mean that both cars are moving with constant velocity? It means that their equations of motion, it's going to be linear equation. Here you go. It's going to be car number 1 has this equation of motion, right? And car number 2 has this equation of motion. I gotta make sure that I put different symbols for x. For x, x naught, and v, right? For each of those cars. First piece of information. Here you go. First piece of information. Those cars are moving with constant velocity. Okay. And the initial positions are known as well. So that's the other piece of information. First piece of information, those cars move with constant velocity, you know. Second piece of information. Second piece of information. No. We know their initial positions, x naught and x naught 2. So that's what we put here. And the third piece of information. Third piece of information, we know their velocities, v1 and v2. v1 and v2. So all those three pieces of information are being used here in those equations, okay? You know, in other words, x is linear with t, okay? So now we're going to solve the problem, right? We also know that, let's see here. Oh, yeah, v2 is greater than v1, right? We also know that v1 is less than v2. What does it mean? It means that x is going to grow faster, x2 is going to grow faster than x1, okay? That's what it means. So we did visualize the problem in PowerPoint with this slide, with this movie, right? So here you go, let's play the movie again. That's the initial position of the cars, right? So one is going faster than the other, but the one that's going faster than the other is behind the other. So what does it mean? It means that eventually it will catch up with the first one, okay? That's what it means. So that's one way to visualize. Three different ways to visualize the problem, right? With the mathematical equations, with this PowerPoint slide, and there is one more way to visualize this problem. There is one more way to visualize this problem. We're not solving that yet. We're just visualizing. We want to picture what's going on here. Another way to visualize this problem is to plot the graph of both cars in the x versus t, the position of the car versus the instant of time of each car, okay? That's another way to visualize the problem. So let me show you how we do that. Okay, we can have the first car. We can plot the position of the first car with time. Okay, in this case, the slope is going to be v1. And then we can overlay the plot of the other car over this graph. So what do I mean by overlaying? Okay. I'm gonna, even better, instead of overlaying, I'm gonna plot separately, you know? Here you go, position of car 1, right? And then we can find the position of car 2 as well. We do know the position of car 2 is, initial position of the car 2 is smaller, right? Than the initial position of the car 1. That's why it's behind. Okay. So instead of x naught 1, now we replace it by x naught 2. But we also know that the velocity of car 2 is less than velocity of car 1. No, it's greater than velocity of car 1. What does it mean is greater? It means that this slope here is going to be steeper, right? And now we're going to combine those two graphs in a single one. Here you go. So you can visualize the simultaneous position of those two cars. Here you go. I'm gonna combine. Here you go, in this graph. Supposed to look like that. Okay. And here you go. I'm even gonna put in different colors, so it's even easier to visualize, right? The one is gonna be, let's say, blue, and I wanna make it thicker as well. Everything here is gonna be blue. Boldface blue. And the other here is going to be boldface red. Boldface red, thicker, a little bit thicker. Here you go. And I'm going to make that red as well. Okay, and then what else I'm going to do? I'm going to extend this graph here. So we know, here you go. I'm going to extend this line as well. I need to extend this line so you can see where their positions are going to be the same. Okay. The position of car number 2 is going to be equal to the position of car number 1 at this spot right here in the graph. Okay, right in here. I can write that down. It's a little bit lower, right? Here you go. I'm going to put this one black and thicker as well. Whoa. Here you go. Here we're going to have x1 equal to x2 equal to x2. Oops. Font. Good script. Here you go. Boldface. I still do not know what's the x1 and x2, but I am visualizing how to solve this problem. At this position, we are going to have this instant of time. The instant of time where the two intersect one another. Okay. And then, I'm going to call that T prime. Call that T prime. Okay. Save it. And now we can go and solve the problem, finish solving the problem. Again, three ways to visualize this problem, right? The first one that we did here was by the equations, enunciating the equations. The other one that I did here for you is by playing a movie, right? Coming up with a movie in which car number 2 is catching up with car number 1, little by little. Okay. And the third way is by plotting their graph, the x versus t. Plotting the x versus t graph separately, right? One is has a different slope, has an initial position that's lower than the other. But because it's moving faster, eventually it will be able to catch up the other one. Here you go. Position, see? And what you see right in here is the distance between those two cars, the display, the distance between each car, okay? This distance here becomes smaller and smaller until it's equal to 0. 3 different ways to visualize the problem, and now we're going to finish this problem using algebra. Okay, the condition is find t for x1 equal to x2. For x1 equal to x2. That's the first. X1 equal to x2, right? You go. Condition. I'm going to put the condition x1 equal to x2 here. X1 equal to x2. And now I'm going to substitute x1 and x2 in this equation. Here you go. Substitute x1 right in here. Substitute x2 right in here. Okay. Use those two equations. So, given two cars in uniform motion moving in the same direction with non-initial positions, I'm going to add with no initial position x1 and x2. I'm going to put n non-velocities. I didn't put this piece of information. It's important. V1 and V2, okay, and non-velocities V1 and V2. Okay, it's important that we put in there so there is no doubt that we know x01, x02, and V1 and V2, okay? And of course that they are moving constant velocity. So let's continue, find t. What I want to find t. Here you go. I'm going to boldface t here to remind you that we want to find this. Please don't forget to, okay. This for linear velocity. Wait a minute, linear positions, Basilio, right? linear position. The velocity is not linear, right? Well, linear velocity is the next topic that you're going to cover. Okay. Yeah. Linear position. Okay, so we go. I don't need those two equations anymore, right? And now we are going to solve for t. We know that v2 is greater than v1. So what I'm going to do, I'm going to pass this guy to the other side. Next step, I'm going to pass this guy here to the other side as well. Is going to invert this sign. Okay. We are going to factor. We're going to factor t on the right side. Let's see here. Strange. Full screen mode. Yeah, there's something missing here. Oh, equations. That's what I'm looking. Okay, that's what I want. Good. Factor it. Go. I don't need to have t there anymore. And we solve for 3t. Right? We solve for t by passing this ratio to the other side. By passing that term, not the ratio, but the term to the other side. We go. I want to put my t on the left side. We solve the problem, solve the first part of the problem. Okay. Now we're going to solve the second part of the problem. We solve this part of the problem here. We're going to find out the position of car 2. The car 2 will catch up with car 1. We found the instant of time. Okay. We found the instant of time. And now we want to find the position. Instant of time that car 2 caught up with car 1. And now we will find the position. Their positions at this instant of time. What do? We just go back, copy, either equation, either x1 or x2, right? We copy x1 or x2. I'm going to copy both of them, and substitute this value right in here. You go here and here to find that position. It can be either one, like I said. Let's do just for x1, and then I do for x2 later on. So I don't overwhelm you, right? What position of car 1 at this instant of time, right? That's what I'm asking. Let's continue solving this problem. I'm going to put everything under the same denominator. Okay, right here. Right, everything under the same denominator. And then we get everything under the same fraction. First under the same denominator, then under the same fraction. Right, so here go. I will put a parenthesis there. Copy. got it. That's algebra, right? Next, I am going to expand those terms. Oops, what's going on here? Okay, I'm going to expand the order. I'm distributing those terms. Why is it doing that? Here you go. I'm going to eliminate the parentheses. Okay, and let's see what we get. Let's see if we can simplify any further, right? Let's see, we have V1. Oh, yeah. See here? We can simplify this term. Do you see that? Right? I want to make it look even cleaner than that. I'm going to commute one term to the other, right? So here you go. X naught V1, X naught 1 V1 minus X naught 1 V1. Okay? So I can eliminate this term. Here we go. And I'm going to put V1 on the right side of X naught too, so it looks nicer. Can I simplify any more than that? There's no way I can do any more simplifications, okay? There's no way I can do any more simplifications here. And then we repeat for X2. Let's repeat for X2 just for the fun of it. You know, since X2 is supposed to be equal to X1 for this very instant of time, we should get the same result. It's going to be a different derivation, but we are going to get the same result unless I made some mistakes. Okay, repeat for X2. Okay, repeat for X2. I'm going to replace T there. Okay, here you go. I am going to put under the same. I'm even going to use the same thing here. See that? I'm even going to use the same thing here and just start changing the subscript. So, you know, so here you go. Instead of X naught 1, there's going to be X naught 2, right? Here you go. X2. It is the same denominator here, V2 minus V1. And I put under the same denominator. Let's see. Oh, here should be V2, right? Yeah. V2, here should be V2. Okay. Here you go. Here is going to be X2. Here should be X naught 2. V2 minus V1. What else? Here should be V2. X naught 1 minus X naught 2. X naught 2. X naught 2. And here it should be V2. V2. Okay, let's continue. Here you go. Oh, don't forget X2 here, right? X2. I'm going to change everything here to X2. So I don't forget to change at the end. Okay, x2, okay, x naught 2, x naught 2, v2, v2, right? X naught 2, x naught 2, v2, v2. Okay, so let's see if we can finish that. Oh, now, okay, it's gonna be slightly different, okay, than the previous derivation. Okay, I'm gonna even show that to you. We have, okay, v2x naught 2 here, right? See, v2x naught 2, you have v2x naught 2 here, and you have v2x naught 2 here. One is the positive sign, the other is a negative sign, right? I even gonna commute those terms. Oh, even gonna commute those two terms. I'm gonna commute this one as well. And then let's see if we get this exactly the same thing. Okay. So here it goes. This one cancels out with this one. And we are supposed to get the same result that we got for x1. Let's see, side by side. Side by side. Okay, so we have x1, x naught 1, v2, right? We have x naught 1, v2. We have minus x naught 2, v1. We have minus x naught 2, v1. We have v1 minus v2, v1 minus v2. Okay, so that's the only, the last step. Let's do here the last step, which is to commute those two terms in the numerator. Okay. So, and then you can go ahead and do some numerical values, right? If you don't feel familiar about symbolic derivation, you can go ahead and do some numerical values in there, you know, whatever numerical value you want. It's 9:45 right now. Any questions? That's the type, you know, that's the type of problem that has a higher level of difficulty, okay? Because it involves two equations. Take a look at how much space it took me to, right? To solve this problem, right?
Professor?
Let's see. 1, 2 lines, 3, 4, 5, 6, 7, 8 lines, 9, 10, 11, 12, 13, 14, 15 lines. Okay. And then you have to account for the other one that you didn't have to do, but it's a good way to check your results. Any questions about that before we go into break?
I had one question. How many questions like this do you think would be on our exam?
Oh, it's gonna be at least one.
Okay, thank you.
Okay. So let's go to our attendance here. 19 today is lab attendance. Oh, lecture attendance. Why do I have 19? Oh yeah, I have 19 here. Let's go for Jade. Jade, are you there? Jade, let's see here. Jade is here. I see Jade here, but she's not answering. I'm gonna put a star here in her name. Vanessa, are you there, Vanessa?
Here.
Okay, thank you, Vanessa. Makin Curto.
Here.
Thank you. Ashley Diaz.
I'm here.
Okay. Fisher Dawn.
I'm here.
Thank you. Blessing.
I'm here.
Erika Fajardo. I don't see Erika here. Janet Garcia. Janet, are you there? I see Janet here in the list, but she's not answering. Good. Next is Raymond Garcia. Thank you, Raymond. Donovan Harris.
Professor, I'm here. This is Jeanette.
Jeanette, okay. Jeanette Garcia, right? Okay, good.
Yeah.
Jeanette, okay, thank you, Jeanette. Lily?
Hi, Professor. I'm here. Also,
Thank-
Michael, my cousin, he's here, but his microphone doesn't work. But I think he just
Okay.
posted on Zoom.
Okay, thank you. Thank you, Michael. Wendy Hernandez.
I'm here, Professor.
Thank you. Joshua Jimenez.
I'm here, Professor.
Okay, Bethany Kirschnick.
I'm here.
Okay, thank you. Luis Latiza. Okay, thank you, Luis. Ana Gabriela Lopez.
Here.
Thank you. Basilio Lopez. Thank you. Daisy Vahag Mart. Okay, Bahar, I can't hear it from you. I'm gonna put a little star here. Let's see. Next, Daisy Mariscal.
I'm here, Professor.
Thank you. Alejandra Marmolejo.
I'm here.
Thank you.
Professor, I just
Yeah.
went to the bathroom. It's a Vahag.
Bahag, okay. Let's go Bahag here. Amarilis. Hi, Amarilis, are you there?
I'm here.
Okay, thank you. Julissa Molina. Julissa, I don't see Julissa here in my list. Yesenia Montes Rodriguez. Okay, thank you, Yesenia. Mary Okeki.
I'm here, Professor.
Thank you. Ryan Ong.
I'm here.
Thank you, Artur Pacheco.
I'm here.
Jennifer Perez.
I'm here.
Levilud Ponte. Thank you. Lydia Rosa. Okay, thank you, Lydia. Pedro Ruiz. Pedro here. I don't see Pedro here. Donia.
Here.
Thank you. Alika. I don't, okay, I see Alika here.
I'm here, Professor.
Okay, thank you. Brianna Valencia.
Here.
Next is Mia Villalobos.
Here, Professor.
Thank you. Justena Youssef.
Here, Professor.
Next, Arika Rice. I don't think Arika is here. And then Kelly, are you there, Kelly? I don't see Kelly either. Now let's see how many students we have. 31. 31 as well. Let's see, there's just one student. What about Jade? Are you there, Jade? Jade is still not answering. Okay, it's 9:55 now. Let's go for our break. Break from 9:55 to 10:10. By the way, just to let you know, I'm finishing. We're finishing the class 15 minutes earlier today. Only today, okay? And I also have to cancel my office hours. If you
Okay.
need to talk to me, I can accommodate you on Wednesday after class, okay? If you need to talk to me today, I can accommodate you on Wednesday.
Okay, Professor.
On Wednesday after class. Okay. Any more questions? One more minute to go. Okay, so I'll see you in 15 minutes. Okay, I'm back here. So we are done with constant velocity, equations of motion for constant velocity. Okay, we are done. There are some examples here that I want you to go through, okay, that I put here in my notes. You might want to work out those examples on your own. 1, 2, 3 examples, okay? And we are done with constant velocity. And now we are going to start talking about average acceleration and another type of motion that is uniform accelerated motion. We're done with uniform motion, right? And now we're going to start talking about average acceleration, and then another type of motion, that uniform accelerated motion. Okay, just remember what we did so far. We talked about position. We talked about average velocity, instantaneous velocity, equations of motion, and now we're going to come up with a new type of concept, a new type of idea that's very useful. It has some important consequences, this idea that's called average acceleration, okay? If average velocity is delta x over delta t, okay, average acceleration is defined as delta v over delta t. What's delta v? Is the change in instantaneous velocity divided by the change of time, okay? So it's just one step further. The definitions are kind of similar, right? It just happened that you're changing the term in the numerator here. It's still divided by delta t. It's a rate of something, right? Here's the rate of change of the position. Here's going to be the rate of change of the velocity. Okay, and we can do dimensional analysis just like we did before. What's the unit of velocity? You should know that already, right? The symbol that you use for dimensional analysis is this, the dimensional analysis is this square bracket. So we go ahead, define the equation for the velocity, average velocity delta x over delta t. So the unit of velocity is going to be the unit of position, the unit of displacement divided by the unit of time, which is meters per second. We can do the same for the average acceleration. Remember, memorize that, okay? What's going to be? Unit of velocity, unit of change in velocity divided by unit of change in time. Okay, and unit of change in velocity is meters per second, unit for time is second, and that's what we get for the unit of acceleration. Whether it's average acceleration, whether it is instantaneous acceleration. We're going to talk about that, right? If velocity is measured, acceleration is measured, how the velocity changes. How position, right? Or displacement changes in time. Okay, now let's talk about a very simple example, right? So let's take the case of an object that is at rest, remains at rest between t equal to 0 seconds and t equal to 5 seconds. What's the average acceleration during this period of time? Okay, question mark here. What's the average acceleration? You just go ahead and apply the definition. Okay, is final instantaneous velocity minus initial instantaneous velocity. The object were at rest all the time. Consequently, the initial and final velocities are going to be 0, right? Here you go. 0 minus 0. Delta t is not 0. Delta t is 5 seconds. And we get an average acceleration of 0 meters per second. In another example, you're moving with constant velocity of 5 meters per second between 0 seconds and 5 seconds. Now it's no longer at rest, right? Now the object is moving with constant velocity. What is your average acceleration during this period of time? So again, so you go ahead, put the delta v there at the top. Delta v is not changing. It remains the same, even though it is moving, right? The velocity remains the same. And the delta V ends up being 0 meters per second, and the average acceleration is still 0 meters per second squared. So for the average acceleration to change, you must have different velocities, different initial and final velocities. Otherwise, the average acceleration, for the average acceleration not to change, for the average acceleration to be greater than 0, okay, you must have different initial and final velocities. That's the conclusion that you get. Okay, if the instantaneous have different instantaneous initial and final instantaneous velocities. Okay, the instantaneous velocity must be different to get an average acceleration that's different, not even greater than 0. Let me elaborate a little bit more. For the average acceleration to be different of 0, okay, because you can also have negative acceleration different of 0, you must have different initial and final instantaneous velocities. That's what those examples are all about. Those examples were just to illustrate that you can have 0 average acceleration. You get 0 average acceleration whenever the final and initial instantaneous velocities are the same. So now, let's see an example, again, a simple example, in which the velocity changes. The object is initially at rest at t equal to 0 seconds, and at t equal to 5 seconds, the velocity is 3 meters per second. What's your average acceleration during this period of time? Try to do that on your own. Okay, you can try to do that on your own, so you can build confidence about this type of problem. I'll give you, let's say, 1 minute to do that. It's not for grade. I'm not grading that, but it's still important for you to try to do it. So just go to the very definition of average acceleration. Okay, we have 1 minute already gone by. Let me show you how you do that. Just straightforward application of formulas. Okay, average acceleration delta v over delta t. Final velocity is 3 meters per second. Initial velocity, the object was at rest, so you have 0 meters per second. And delta t is 5 seconds minus 0 seconds. Okay. You do the math here, 3 meters per second divided by 5 seconds. You get 0.6 meters per second squared for the acceleration. Okay. So one more simple example. Let's make one more simpler example. And I'm just going to invert here, at t equal to 0, your velocity is, see, I'm going to invert this problem, okay? Your velocity is 3 meters per second. And 5 seconds later, you come to rest. Oops, yeah, to rest. What is your average acceleration during this period? Okay. I have the equations here, but that's not the right result, right? Because there must be some changes that you have to make. Okay. Solution. 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 Go. Here you go. Delta V over delta T. Okay. Final velocity minus initial velocity. The final velocity is what? 5 seconds later, you come to rest. So that should be 0. But the initial velocity is what? It's 3 meters per second. Okay. So what you end up having is the same magnitude, but with the opposite sign. You go. So this example shows that we can have negative acceleration, negative acceleration values. Okay, minus 0.6 meters per second square. That's what we have for acceleration. Okay, so those are the ideas you have discussed, and now I'm going to add another idea in the same way that I added the idea of instantaneous velocity. I'm going to add the idea of instantaneous acceleration. And from there, I'm just going to repeat what I did for the velocity. I'm going to get the equations of motion for constant acceleration. See that? Here you go. You just finished the equations of motion for constant velocity. We're going to have equations of motion for constant acceleration as well. Okay, so here you go. If instantaneous velocity is the limit as delta t goes to 0 of delta x over delta t, then instantaneous acceleration is going to be also the limit of delta t going to 0, okay, of delta v over delta t. I'll go even further, okay? I didn't do that here in this illustration, but limit of delta t going to 0, limit of delta x going to 0 as well. As delta t goes to 0, delta x goes to 0 as well. The same thing happened here for the velocity, right? Now, what we're going to do next, we are going to get the equations of motion for the case of a particle undergoing constant or uniform acceleration. Okay, why is it important that, it is important, this type of motion. This type of motion is important because it has some practical applications, okay? That's why we study that. We don't get that from anywhere. In the case, for instance, of this object here under free fall, my coin, right? You go, or even this little plug here, those objects, whenever they are under free fall, they are under uniform acceleration too, okay? That's why we study that. Okay, and then we can go ahead and get the equations of motion. Okay, so we go ahead and start just like we did before. We did for the velocity, remember? But instead of getting v equal to constant, now we're going to use a equal to constant. Okay, if the acceleration is constant, the average velocity, the average acceleration is going to be the same all the time. It's going to be the same throughout the motion of the object. And we get, delta v over delta t. Okay, not delta x over delta t, but delta v over delta t. And delta v is what? Final velocity minus initial velocity divided by t minus t naught. T naught is the initial instant of time, which most of the time we can set equal to 0. V naught cannot be set equal to 0 most of the time, okay? You saw the case in which initial velocity was not zero in the previous example. But the initial instant of the time, yeah, we can set equal to 0. So here we go. A equal v minus v naught divided by t. Don't forget that's what we have here is final velocity, right? The final velocity that I neglected, that I renamed it without the subscript. Okay. So here we go. Let me get that. A equal to h of t, v equal to f of t, and x equal to g of t, right? That's here you go. That's mathematical notation, right? A function of t. Acceleration is this acceleration here because it's constant, it's not dependent of t. But we still write that down as though it has a dependence of t. And now we are going to find out that by solving this equation here, we can get here you go, step by step, right? We can get our first equation of motion, that is v equal to v naught plus at. Okay, note the following. Here you go. For constant velocity, the position is a linear function of time, right? For constant velocity, it's / uniform motion, right? Uniform motion, comma. Note, now we have the other case for constant acceleration, which we call uniformly accelerated motion. The velocity is a function, is linear in time. It's linear in time. It's better to write that down here. It's linear in time. Okay, so we go ahead and write our first two equations of motion for uniformly accelerated motion. Here you go. The acceleration is constant. What does it mean to be a constant? It means that it has a constant multiplied by the instant of time t raised to the 0 power, right? 0 power, anything raised to the 0 power is going to be the number 1, equal to 1. And now we got our second equation of motion, v equal to v naught plus at. Okay, one example, here you go. One real life example of uniformly accelerated motion is the case of an object in free fall. An object in free fall. Okay. So what else do we have to do? Okay, you gotta erase that stuff here, right? So we're gonna go to the next step now. Now we will derive the position of the particle, the function of time for a uniformly, or derive the position of the particle as a function of time for the case of uniformly accelerated motion. Okay, we already did the A versus T. We already did for V versus T. Now what about X versus T? How can we get the equation of motion for X versus T? Right? So it comes next here. Here you go. Let me erase that. Now we find what's the function of x with respect to t, okay? There's a little neat trick here. We go ahead, we go back to our definition of average velocity, okay? We go back to our definition of average velocity, which is delta x over delta t. But let's not forget, okay, this velocity right now is changing as time goes by, right? Delta x over delta t is x minus x naught over t. Okay. So that's the first conclusion that we get. Now, there's a little trick here, interesting trick. There is another definition for average velocity that I didn't tell you yet. Okay. There's another definition of average velocity I didn't tell you yet. And this definition is the following. It's going to be final velocity plus, not minus, initial velocity divided by 2, right? Do you recognize this definition? You take the average of two quantities, right? You sum them and divide by 2, right? You take the average of 3 quantities. What do? You take the sum of all those 3 quantities and divide it by 3, and so on. In our case, all we can do here is to take the initial velocity, sum with the final velocity, because we have 2 quantities, we divide it by 2. Okay. So now we have 2 definitions of average velocity that we will be able to use to get our equations of motion. Okay, so here you go. That average velocity. So here you go. This definition of average velocity, this other definition of average velocity. Those are 2 independent definitions of average velocity. Okay. Now I put them side by side. What can I do next? Okay, I'm going to make this guy here, this definition of average velocity, equal to this other definition of average velocity. That's what I'm doing right now. What you see writing here is this definition of average velocity. What you see right here is this other definition of average velocity. Okay. And then what else? You go, I get x minus x naught. I'm passing the t to the other side. Average velocity times t, right? And I'm about to get my equation of motion in terms of x. Okay, so here we go. But before we do that, what else do we do? We recall our first derivation that we got right in here. Remember? Constant acceleration results in what? A linear change in velocity. That's what I have here. Okay, I don't need that, right? I can erase that here from. And then what do we do? Don't forget, this equation here is for the final velocity of the object. I go ahead and substitute it here. Okay. I substitute it here. You can do that on your own. I'm going to do that myself too, otherwise I get bored. Here you go. So you can see that in real time how it's done, right? Here you go. X minus x naught equal to v naught plus v plus v naught divided by 2 times t. Okay, here you go. I will copy that here, place it here. Okay, so go ahead. Very important that you do this derivation yourself as well. V naught combined with this other v naught becomes 2 v naught. Okay. Notice that I have a t term here, and I also have a t term here, right? You notice that? Now I'm going to expand this term. Okay, this guy is going to become v naught t. Plus at squared. Okay, and that's what we get. Equal x equal to x equal to x minus x not equal to v naught t plus half at squared. Okay, and x naught plus v naught. Do you see what we get here now? We get a second order polynomial for the position. I can now just erase that. Same equation. So equations of motion. Equations of motion for, I'm going to do a table here. So you can see insert 1, 2, 3. Position. Well, let's do that together. Equations of motion. Yeah, here you go. Uniform motion. Uniformly accelerated motion. Okay, so here you go. I need to put 3 here. Acceleration. You should know what would be the acceleration for uniform motion, right? Okay. Acceleration for uniform motion is 0. Okay, acceleration for an object under uniform acceleration motion is constant. Constant. Okay, for V, our object under uniform motion, has a constant velocity. An object that's uniformly accelerated has a linear relationship. The velocity has a linear relationship with time. I'll put that all. And then here you go. Equations of motion. I can even make it look nicer. Here you go. Equations of motion. And then finally we have position x. X is what? Go back. I'm going to even copy what I have here. X naught plus vt. And now for uniformly accelerated motion, I'm going to put that different of 0. Different of 0. Constant difference of 0. Okay. Linear here, right? Constant here, constant here. I can even write that down, constant difference of 0 as well. Constant difference of 0. Linear here, linear here. Okay. And then we graphs, graphs for uniformly accelerated motion, right? you have A versus T. A versus T. You have the graph V versus T. You have the graph Vx versus T. Okay, so here you go. Let me see if I can show you the graphs. That's for, let's see here. Okay. In general, you can have this type of graph, okay? But I want to, let me see if I have it here. There is, yeah, I don't have a graph for uniform accelerated motion. I have to build that from scratch. Okay, I'm gonna use this one here. Okay, V versus T, uniformly accelerated motion. What we have here? V naught. Okay. V versus T. I don't need that drawing here. Here, the slope is going to be A. It's not X versus T, it's plot of V versus T for uniformly accelerated motion. Okay, that's what it should look like. And then if you plot X versus T, it's going to be different. Plot of X versus T for uniformly accelerated motion. Okay, here we go. I can it's gonna look like a parabola, right? So let me see if I can get that. Yeah, here you go. It's gonna look like something like that. If it will look like something, and instead of X V naught here, we must have X naught here. Here you go. Okay. Make it thicker. It looks nicer, to make it look nicer. Note C. Okay, graphs, right? Let's make another graph. Let's make the I did for V versus T, right? And I can also do the graph A versus T. Here you go. A. Don't forget the unit here. The correct unit should be for meters per second square. Superscript A. A should be constant, right? I don't need that. Here you go. Here's supposed to be meters per second. V is linear. And the X versus T looks like a parabola. But there is more to it. Is a parabola, right? Plot of V versus T for uniform accelerated motion is a straight line. Okay. So another example, right? See here. Yeah. First graph. The first graph is a horizontal line. The second graph, a straight line with a slope, horizontal line with 0. With a slope equal to 0. The second graph is a straight line with a slope different of 0. The third graph is a parabola. The parabola. Its concavity can be either up or down. Its concavity can be either up or down. Either way is still a parabola. Any questions so far? Let's elaborate a little bit more on that, right? So let me take this jacket here. I'm getting hot.
Professor,
Yeah.
could you
Go ahead.
draw a parabola like through Excel, like Microsoft Excel? Is there a way? You know how you taught us how to plot points, make a graph?
Yeah.
Can you make a parabola in Microsoft Excel?
Yeah, I can do that right now. Want to see it?
Yeah.
Good.
Thank you.
Okay, so let's plot a parabola here. A real parabola, right? What I did there is not a real parabola, but it's close enough. But if you want to plot a real parabola, here you go. Let's go here in Microsoft Excel, right? So here you go. It's gonna be, here you go. I'm gonna do plot. Let's do an example, right? And then we plot the example here in the Excel. Okay, so here you go. Example. You know, example. Let's see. Yeah, example. Let's do an example. Example. Plot. Let's see how I'm gonna do that. Let a car have an acceleration of 1 meter per second square, right? Along the positive x-axis. Okay. X-axis. Its initial velocity is 0. Okay. Write down, do the following. Do the following. 1. Write down its equation of motion. It's 3 equations of motion, right? Of motion. 2. Plot the acceleration versus time, right? And let's see, write down its equation for plot is acceleration versus time for, you know, t greater or equal than 0, less or equal than 5, right? Plot the velocity versus time, right? For the same time interval. Plot the not acceleration, the position versus time for, right? Solution, right? Let's go. Here you go. Here's the equation of motion, right? There are three equations of motion. The solution, right? The first one. Why there are three equations of motion? Because the first one is the acceleration, right? And the equation of motion for the acceleration is going to be 1 meter per second squared. Just that, nothing else. That's the first equation of motion for the accelerate for uniformly accelerated motion. The second equation of motion is going to be for the velocity. You go v equal to v naught plus at, right? Did I say something like that? Its initial velocity is 0, right? Its initial velocity is 0. So I have to replace v naught with 0 here. 0 meters per second. Acceleration is 1 meter per second squared. And I go ahead and simplify this equation. You go like that. I'm gonna here write it to make it look cleaner. Here you go. That's the equation for the velocity. Part one, right? I'm doing here part one. And the third equation of motion, we go ahead, get it from our table. Make sure you memorize that. It's easier if you memorize, right? X equal to x naught. And then what else? There's one more piece of information I didn't put here in my example, right? Along the x-axis, its initial velocity and position are 0. Okay. So I need to write that down as well. I need to state that the initial velocity and initial position is 0. So here you go. Here it's going to be 0 meters. Here is going to be 0 meters per second. And here is going to be 1 meter per second square. Okay. That's the acceleration term. You're writing that cleanly, and here we go. We get something like that, and I just write x on its own. Here you go, ½ meter per second. So I can take this guy out of here. ½ meter per second squared t squared. Okay, so that's part one. And I'm going to do part 2 in Excel, part 2, 3, and 4 in Excel, right? Part 2. Okay, see graph in Excel. This first one is going to be easy. Okay, so here you go. We want to plot A, put between parentheses meter per second square. You can do that as well. Make sure you do that in Excel as well. Let's see, font right in here, superscript. Huh? Now go, I'm going to bold face it to make it look nice. I'm going to put T here as well between parentheses second. We start at 0 seconds. I'm going to go ½ by ½ seconds. Half, 1, and now I'm going to all the way up to 5 seconds, right? 3, 4, 5, here you go. Format cell with a single decimal place. I don't need more than that, okay? And I know that the uniform acceleration, right? Because it's uniform acceleration. And by the way, it's going to be 1 all the time. Okay? And by the way, we should put the A to the right of the T, right? I'm going to plot that, and you should get a straight line in the horizontal direction, not this one, insert chart, right? And I'm going to put a straight line here. Let's see here. I'm going to do that all over again. insert. Now, this one I can put a straight. Here you go. Oh, not good. Huh, interesting. Okay, I'm just gonna do is let's see. This one that I want. Okay, here you go. Okay. That's my first graph in Excel, right? The next graph is going to be for the velocity. In meters per second. And the equation is going to be what? It's going to be AT, right? Let's go back to the equation. The equation is going to be, blah, 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 here you go. The acceleration A, 1 meter per second, times T. Okay. So going back to our graph, it's going to be 1 times T. 1 for the acceleration, and this cell here for T. I put an equal sign here. And now I have my genetic equation there already written down in the cells of Excel. I can plot this graph, right? V versus T, and insert. Here you go. Now we have our, even better, I want to put this straight line there so you can visualize the straight line more easily. Here you go. You don't do that in the lab, right? You can do that only in the lecture. And then don't forget to put the labels, V meter per second, T in second, right? And now what you asked was, the position, right? The position that you're going to get the parabola. X is going to be in meters. And the equation, going back to the equation here. Here's the equation. Half the acceleration times T squared. Okay? Half the acceleration times T squared, going back here. Half the acceleration, and the acceleration is 1, so I have to 1/2 the acceleration. We're going to have half, times T squared. Okay? Now click and drag. You're going to learn how to do that in the during the course, right? Let's see, number. Here you go. Now that's the graph that you asked, right? I'm going to plot X versus T. Insert. And how does it look like? Look like a parabola. I can even fit a parabola there. Add trend line. And it's going to be a perfect display polynomial right in here. Set intercept. No, interesting. I don't want a linear, I want a polynomial. Here you go. Display equation, that's what I want. Here you go. Now I display the equation. Notice that Excel, for some reason, is putting this very small number here, right? It's 10 to minus 14, 10 to minus 15. For all practical purposes, what you have here is 0. Okay? Do you want me to repeat that? Did you follow how I did that? Okay. So that's how it looks like. I'm going to adjust this axis here. I don't want it starting at -2. I want to start at 0. Here you go. Better. Okay. Okay, so now one more other thing that you gotta know. C graphing Excel part 2. Yeah, C graphing Excel part 2. Parts 2, 3, and 4, right? Parts 2, 3, and 4. C graphs in Excel. But if you don't know how to use Excel, right, you should know by heart from math, from your math course, how to plot those things. Okay, just like I did here in PowerPoint, my PowerPoint slide. Here you go. Here you go, could be a little bit more. Like that. What else you have to know? Okay, so here you go. Let's see. Now we're going to do something slightly different. Like, let a car having an acceleration of not 1 meter per second square, but minus 1 meter per second square along the meter per second square. And initial velocity. Now it's a little bit of a difficult problem, okay? 1 meter per second and initial position of 0. Initial position of 0. Just repeat what we did before. Okay? The difference here is now that my acceleration is going to be minus 1 meter per second square. It's going to be an important difference, this minus thing here. Okay, so write down is 3 equations of motion, just like we did before. Here you go. Part 1, I'm going to take advantage of those 3 equations that I have already written there and just change accordingly. Minus 1 meter per second square. Okay. The initial velocity is 1 meter per second. Okay, V0 is 1 meter per second, and acceleration is minus 1 meter per second square. So that's what my equation of motion looks like for the velocity. I just here write that down here. Okay. Repeat that for x naught, for x, not x naught, but x. Here you go. X naught plus V naught t. Initial position is 0, but initial velocity is not 0 anymore. It's 1 meter per second. The acceleration is negative, so I'm going to put the negative right in here in this number to emphasize the fact that that term in the parentheses is going to be the acceleration. Okay, and now we can here write that like that. Write it like that. We do not need the 1 here anymore. I don't need to emphasize the fact that's positive, right? And I write the final equation like that. Now let's plot this graph. Let us plot this graph. I'm gonna, you go. A minus 1, you go, V like that, and X like that. Final equation. Let's go ahead. Now it's going to be a different plot, right? Remember, this plot here was a positive acceleration, right? Because it was a positive acceleration, you got a curvature, a parabolic curvature that's upwards. Now, if you have a different type of graph, let's see, let's go, I'm gonna copy that, I'm gonna paste it here, here you go. Now it's gonna be -1, right? Go, -1, -1, and so on. The velocity is gonna be different, it's gonna be +1, you know, -80, right? That's what we get for the velocity. And I'm going to make a movie as well of this the position of the velocity of this guy, okay? And then what about x? X is gonna be -half t squared, right? Here you go. I'll write down -half. And by the way, we still have the velocity, you know, which is gonna be 1 times t minus 8t squared. Half 8t squared. Let's plot each of those graphs separately. Now, you know what? I'm going to just plot this one here. Okay. So you don't spend too much time. This one is simple, right? This one is simple to plot. It's going to be just a horizontal line below the x-axis. This one here is going to be a parabola. Yeah. It's going to be a parabola, but it's going to be a parabola, a downward parabola, with a concavity downwards. I can even, you know, add the trend line to this graph. It's going to be a polynomial. The equation is going to be displayed. Okay, just like before, Excel is putting, yeah, Excel is putting this very small number here, see that? Half 8t squared, right? Plus VT. The X is in reality, you know, is the T, right? I'll put it here, emphasize that you gotta do the same in the other one. It's not half x squared, it's half t squared, right? You go. And it's not y, in this case, it's gonna be x, right? Same there, x. And then I have to fix the other one. Do you see what's happening if you have a negative acceleration? The concavity is gonna be downwards. 11, 10. Let me summarize here in my notes. Okay. Final equations. Part 2, 3, and 4. See graphs in Excel. See graphs in Excel. Note the following. When the acceleration is negative and the concavity of the x versus t graph downwards, right? Downwards. And because the acceleration is also negative, let us plot the other graph for the velocity. Here you go. This graph here for the velocity. I didn't plot that for you. Let's plot it. because the acceleration is negative, the velocity here is going to be you're going to have a negative slope as well. Okay. So here you go. So a trend line, linear. Display equation chart. Okay. So here you go. Display the equation. Y is going to be your velocity. X is going to be t. Okay. Like that. And I can even go, further, right? And plot the graphs in the way they're supposed to plot with the labels and things like that, right? Let's see here if we can get that format. Chart design, add elements, axis title, primary horizontal, t in seconds, primary vertical, v in meters per second. And I can repeat for the other one as well. Here you go. Chart design, axis title, primary horizontal, t in seconds, and primary vertical, x meter. Okay. What else do we have to know about those graphs? Well, we can take a look here at this parabola, right? Initially in this parabola, the velocity, not the velocity, the slope, the tangent to the parabola is positive, right? As time goes by, because the acceleration is negative, the acceleration makes the velocity become smaller and smaller. At this very point here in time, the velocity is equal to 0. Because this, notice that the slope becomes 0 as well. And then as time keep on going by, then the velocity inverts the direction. The particle inverts its direction. I can even plot, let me see here. Yeah, I can even make kind of a, yeah, I can even come up with what we call a motion diagram. And it's not going to work well, but let me see. It's going to work well in the other one, not this one. A motion diagram in Excel. I can do that too. Okay. Note that the particle, here you go. That's a positive acceleration, right? I'm going to come up with a, oh, what's going on here? Here you go. I'm going to come up with a motion diagram. Okay, that's, I'm going to do that. Yeah, this guy will stay here. Yeah, and I'm going to do like that. I'm going to label it Y, and I'm going to make it 0. Okay. A motion diagram is going to look something like that. Okay, here you go. Do you see? Each of those dots here in the graph is half of a second. At time t equal to 0, the particle position is 0. At time t equal to half second, the particle position is 0.13 meters. Okay. At time t equal to 1 second, the particle's position is half meter, and so on. Do you see the spacing between each dots here? They grow larger and larger. That's because the particle is undergoing uniformly accelerated motion. And what you see here has a name, it's called the motion diagram. Okay. 11:15 right now. Any questions about that? Okay. Yeah, let's take another break. You know what? Yeah. Let's see, there's a message here. I can't hear you. Okay. Is everybody, can you all hear me? Do you have any problems? It looks like Yesenia has a problem there on her side. Anybody else? Can you all hear me? Well, yeah, okay, good, thank you. Okay, so if you're not hearing me, that's because, well, if you cannot hear me, it makes no sense for me to talk, right? But thank you for letting me know. Okay, so let's write that down. What are we gonna do? You know what? Let's go for 15 minutes straight without a break, and then we finish half hour earlier, so we don't have our 15-minute break. Let's do this way. Another 15 minutes here, right? Here is the schedule, right? We're not gonna have a quiz today. Okay, I want to finish this chapter 2. Okay. Downwards. Motion diagrams, right? I didn't mention about motion diagram. I start mentioning only right now motion diagrams. What's that? What's motion diagrams? It's a depiction. A motion diagram is a depiction of the position of the particle at different instants of time. Okay. For a particle undergoing uniform motion, okay, the position of the particle is evenly spaced. Okay. For a particle undergoing uniformly accelerated motion, the position of the particle increases or decreases depending on the acceleration. Okay. The distances, okay? They put the distances. You already saw a motion diagram for the, here's an example of a motion diagram. I'm gonna copy that and paste in my notes. I'm also going to, gonna put a axis title here in this case. I'm not gonna put anything for the y-axis because it doesn't matter. Okay, here, and snipping tool. Here's the snipping tool. Here you go. I'm gonna capture this thing here and paste there. Here you go. My motion diagram for motion diagram for a uniformly for particle undergoing uniformly Accelerated motion. Okay. Okay, so you can see that the distances, right, keep on increasing as time goes by. You know, each dot represents the time separation between each dots, the time separation between each consecutive dot is half a second. Motion A equal to 1 meter per second square. Okay, oops. Is half a second. And I'm going to do the similar one for uniform motion, right? So here you go. I'll copy this one here. Okay, here you go. T. Now this one is for uniform motion. And go equal, let's say 1 meter per second, okay? 1 meter per second, initial position equal to 0. Here you go. And I also need to put a plot here. Just like I did for the other one. Insert. Okay, that's the motion diagram for a particle undergoing uniform motion, constant velocity. Chart design, axis title, primary horizontal, x parenthesis meter. Okay. So notice that, you know, the separation between each dot is the same. So let's go get the graph, just like I did that. I'm going to place there in my notes. Okay. Motion of a particle undergoing uniform motion for V equal to 1 meter per second, for V equal to 1 meter per second. The time separation between consecutive dots is half a second. So compare this difference between one and the other, okay? Particle undergoing uniform motion, particle undergoing uniformly accelerated motion. That's what we have for this chapter, okay? So let's summarize, you know, definition of average velocity, definition of instantaneous velocity, right? Equations of motion for constant velocity. That's uniform motion. We call that uniform motion. What else? Definition of average acceleration. Definition of instantaneous acceleration. Equation of motion for constant acceleration. Uniformly accelerated motion. like that. Okay. Graphs A versus T. You know, and I'm going to even put it here. No, left it this way. A versus T. V versus T. X versus T, right? And also what we did, motion diagram. So we covered all that stuff here. That's what the summary of what we did for chapter 2, right? One-dimensional motion. Will you be posting the Excel graph for the equation along with the notes? Yeah, I can do that. Yeah, I can do that. Here you go. You can get that save as. Let's see. The equations, I'm going to post the Excel graph there. The equations are going to be there. Okay, if you want to learn. Yeah, if you want to learn how to. Let's see here. I won't put that first graph. Let's see. Okay, this one you're going to see later on. Constant acceleration. Let's see here. Let's see. Okay, this one's going to be next time we meet. Insert. So that's going to be 9/26/22. Okay. I don't need to know that, right? Motion. Now I'm going to save that as Adobe, as PDF, not Adobe, but PDF. Now let's see. This graph here. Let me see here. Okay, they are all. How do I want me to label that? Let's see. I didn't post this one, did I? I'm gonna post this one as well. Uniformly accelerated motion. And how they call it? Motion diagram. Motion diagram is just like we can say that motion diagram is just like frames of a picture of a movie, right? That's what you have in the motion diagram. You have frames of a movie picture, moving picture, right? Here you go. Particle is initially here, later on it's here, and so on, blah, 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 right? That's what this graph is all about. They are frames of a motion picture. And I'm gonna post that right now. Documents, backup, LAHC colleges, Harbor, 2022. Let's see if yeah, I have it here. I'm gonna post this one right now. Google Drive. You can play with the numbers, with that spreadsheet. You might want to play different velocities, right? Different velocities value. It helps you understand how those equations look like, right? Uniformly accelerated motion and, oh yeah, I put the graph Prassi there, right? So you do have the graph Prassi. And what else do I need? I need the notes. Here you go. Okay, upload, replace it. Okay, so you have the latest files in there for the notes. Well, let's see how it goes, Bethany. Let's see how it goes, right? We're already a little bit behind, right? Will you have enough time to cover up the chapter 4 for this? I do not know. Let's find out. But if you don't have, it's going to be just chapters 1, 2, and 3, okay? I came in a while. Oh, but okay, let's see. Any more questions? Okay, so if you don't have any more questions, let's finish it now. And I see you again on Wednesday, right? For the continuation of our first lab. We are finishing earlier only today, right? Well, next time will be the whole 3 hours here, 3 hours and 10 minutes here. Okay, thank you all.
Professor,
Yeah.
so I was the student last week that asked you about the different edition of the book. I know you said come to your office hours, but I have class during those times, so I'm not able to attend. Would it be possible if you can just let me know and tell me for Wednesday? Like you can look right now, or not right now, after.
So you want to meet me on Wednesday? That's what you said?
No. I won't be able to meet after class because I have class afterward on Mondays and Wednesdays. So I wanted to ask if it's possible you can look and see if that edition of the book is okay, so I wouldn't be able to, so I won't need to purchase the Wiley Plus.
Okay, yeah, that there are two things here, right? Two things here they have to worry, right? The edition of the book is fine. Okay, if you got the same book is a different edition, is that right?
Yeah, I think it's 9th edition. Like ours is 12th, and you said you said I think
that's not a problem. That's not a problem. The book doesn't change much. Okay, that's not a problem at all. Okay, the next question is Wiley Plus. Okay, we need Wiley Plus to do the homework. Okay, you do the homework online and you get a grade for the homework. That basically that's what the Wiley Plus is all about. Okay, so if you want to get credit for the homework, you will need to have access to Wiley Plus. Okay, it's only 10% of your grade.
Okay. All right.
It's not that expensive. Okay, it's only $69, and I have seen platforms like that cost like $100. So we got a good deal for you there.
Okay, and just have one more question. When will the recordings be posted?
The what? Recording? Yes, I have already posted 2 recordings there. Okay.
On Canvas, I wasn't able to.
No, it's not on Canvas. It's on my. 1 minute. Let me stop recording here first. It's not on Canvas. It is on my YouTube channel. Did you check my YouTube channel?
Yes. I remember you said it last week. Okay.
Yeah.